Hello and welcome back. So in the last episode, we continued work on pointers, and in particular, we managed to add dynamic memory allocation. This is fully memory safe. So here we have a use after 3 followed by a double 3, and we get a panic here on line 21, which is this use after 3. This is because we're keeping track of all allocations, so we can query whether a pointer is still valid. And if we comment it out, so now we're having a double 3, we're getting a different panic that we have an invalid heap address, and we get like the full code stack here. So that's nice. The plan today is to continue and add more pointer operations, in particular pointer arithmetic. We currently do not have it, so we want to support it, but pointer arithmetic requires knowing the size of the types. So you don't increment the pointers in bytes, but by the current size of the type. So we want to add the ability to query this. So we want sizeof and alignof first. So we want, then we can also do like sizeof int. So we want to support that first. Okay. So sizeof is actually interesting because sizeof you can do like in size of int, and then you can do the size of int. Or you can do, as you know, size of 42, size of 42. So the operand is both type and an expression. And in particular, if it's an expression, the parents aren't actually relevant, right? It's just a unary operator. So this is the same, similar to how you would write plus 42 or right? This sort of parents. Sizeof actually doesn't need the parents here. So let's look at the standard. So this is what I mentioned. Sizeof is a unary operator. It takes a unary expression, so without parentheses. Of course, like a unary expression is a parenthesized expression, so this is where the parents come from. Or a type name, and if it takes a type name, it's always in parents. And similar alignof, it didn't repeat this weird behavior where you can have both an expression and a type name, only accepts the type name. And semantically, there is some constraint about incomplete types, obviously, and then sizeof just yields the size in bytes, and alignof yields the alignment. There is sizeof crucially does not evaluate the expression unless it's a variable length array, but we're not going to support those. So it does not evaluate the expression, so the expression operand doesn't matter. And then it returns unsigned integer type size t, which in our case is unsigned int. Okay, so let's add that. So we want a new kind of constant expression. So a sizeof or alignof expression. And this is, let's call it a type constant expression, because this is a constant expression that returns like a constant based on some type. So this is a basic node kind type constant expression inheriting from expression. The operand is type. And then we've got like an enum. Let's just call it opt, similar to how we do unary operators. So it has an opt, which is uint 16, and then we can reuse, yes. So it's a uint 16, and it can be sizeof or alignof. Okay. The constructor takes the boilerplate, a type, and which sort of operand it is, and then the operand type. So node base takes constructor and type, and the type gets the operand type. Then we can leverage heading bytes in the base class to store the opt. So opt impl set op impl to op, and we want to always want an unsigned int. So let's add a precondition for that. That the type casting it to built-in type kind has to be built-in type uint64. Okay. Ideally, we wouldn't like take the type arguments, but because we cannot construct the type without the context, we have to pass it in. Okay. Then we want to expose the operand. Why do I copy paste it? So opti op. So what we're doing is returning that one, and then we want to get access to the type operand. So const type. How do I have? Unit expression has like an op and a child. This isn't really a child. So let's call it the operand type. All right. I need, since type is also a member in the base class, I need the namespace name. Okay, so this is a type constant expression. We need to add that here. And then follow the compilation errors. So type constant expression, type constant expression, type constant expression. And then when we want to print it specially because we want to print the type, actual type. So what we want to do is we want to just dump the operand type. Okay, so let's add it to the parser. Now the standard says that this is part of the unary operators. Let's also ignore this version, so let's focus on this one. This is a unary expression according to the standard. But this doesn't so the way we are parsing things with Lexi. A unary expression cannot take as an operand something which isn't itself an expression. So we cannot pass them, so we cannot add them as new unary operators here, like we handle the other ones, because then the operand would be an expression and not a type name. So we actually need to pass them here in the primary expression parsing code, because here we can pass arbitrary things. This should be completely fine, because if we're parsing a unary expression, we implicitly also parsing a parenthesized. So sizeof, alignof are technically unary operators, but we can't pass them here since their operand is a type and not an expression. It should make no difference. However, okay. So we're passing them at that point. Let's add new keywords. So sizeof, alignof. We also need to reserve the keywords here. So can be sizeof, can be alignof. Okay, right here. So sizeof expression. The idea is when we are having the keyword sizeof, we want to pass a type name. So we're ignoring this version. So we want to pass a type name in parentheses. So we are passing an open parenthesis, and then we're already having this type name in cast right here. Language is a bit buggy because of the expression. So we already have this production type name in cast, which parses a type name followed by a closing paren, which we can reuse. So let's rename that to type name in parents. Parenthesized open followed by type name in parents. And then similar for the alignof expression. Okay, and then we are having a parenthesis sized expression, or a sizeof expression, or an alignof expression. We also, so this takes care of the parsing, but to produce the value, we need to distinguish between sizeof and alignof. So we need to produce a value here when we do that. So actually, instead of making them keywords, we are using a symbol table. Carry type constants symbol table, which returns type constant expression operand, and then we are mapping sizeof to sizeof type constant expression sizeof, and then we are mapping alignof to type constant expression alignof. As usual, this breaks clang format. Okay, and then we are reserving those ones as a literal set, the type constants. I don't like the name here, so let's maybe call it like type ops. Yeah. And so type constant expression is now a symbol from that table. And the advantage here is that when we pass it, we get the value. So we know whether we're having a sizeof or alignof. So carry type ops. And then we also want position information here. Okay. And then we're passing a type constant expression like here. And then we just need to add the callback. We're having a bunch of callbacks that carefully. So this is the cast expression or something. So let's add it right here. So we get the compiler state. We get a position. We get a sizeof type constant expression of. And we're getting a type from the type name. So this returns us the type already. And then, so let's also call this operand type because the actual type is size t. So we're creating built-in type un64. And then we're returning state as create a sizeof type constant expression at the position with that type, that operand, and that operand type. And now we can test. Let's test this. So we have sizeof int. This should pass if we implement everything correctly. So we've got main, function call expression, identifier expression, and the argument is a type constant expression. We should print what it is, not just the type. So which expression up, and then we are printing sizeof, and here we're printing alignof. And like so. Let's add space here. So now the argument is here, sizeof signed int 64. Okay, which is correct. And then we are crashing because we are don't generating any code for it. So let's handle that. So integer constant expression right here. So let's handle it here. Type constant expression. So we need to get the type of the operand. Cogen type. So we're having the type, and then we're switching very straightforward over the operation that we're doing. If it's sizeof, we are pushing its size onto the stack. Love type dot layout size. And if it's alignof, then we are getting its alignment. Pushing that onto the stack. And that should be it. So it compiles, and we're still getting the thing with the double free. But crucially, somewhere in main, right here, we're calling malloc with the literal 8. And there is no 8 anywhere in the source code because this is coming from sizeof int. Okay, and just for fun, what happens if we want a short? And remove this thing. We are getting a panic at line 16 because we are assigning an int to a memory location that only has enough space for a short. So good job. We also want to support this version though to be standard conforming. So we need to tweak the parser a bit, where we're passing the atom right here. So this supports sizeof. Like ideally, we would then add like sizeof here as a new operand, but then we cannot do looker ahead here to distinguish between a sizeof. So we need to distinguish whether it's followed by an expression or type. So it's better if it's handled in here. So we either pass a type name in parents, or we passing an expression with which may or may not have parentheses. So type constant operand in parents. So when we're having a parenthesis, so when we're the parents, we're either passing a type name in parents, or if that didn't work out, then we're passing a unary expression. This can be done, I believe I've added some sort of I already have a rule for that. So recurse and we pass a unary expression. Which now, because we are in parents, we are the operand is an arbitrary expression. Okay, followed by a closing parenthesis. Pass type name or expression as operand of sizeof. Can I make the auto format a bit nicer here? Maybe so? Yeah, that's fine enough. Constant operand unary is just a unary expression. Pass unary expression as operand of sizeof. And then here we're passing type constant operand in parents, or if that fails, then we're passing type constant operand. Yeah, just I don't need that helper recurse, and we just pass a unary expression. Like so. Okay. And now we're getting the need to add a different overload here. So the second overload, this returns an operand expression, And we were asked to get the size of alignment of that expression. But since we are not evaluating the expression, we can just throw it out and directly query the type, because that's the only thing that matters. And now this should still compile and result in 8. So as we can see, type constant expression of assigned in 64, which is the type of 0, which then still results in 8. Right here, 8. But we are also supporting a line of 0, which is not allowed. Because only sizeof can take an expression and not alignof. Alignof can only take a type. So we need to handle that case and say if operand is not of type constant expression sizeof, then state log an error on a sizeof can take an expression directly. Annotation primary at the location of the operand. Let's be fancy. Of the operand expression here, and then we finish that diagnostic. And now we should get an error. Right. Only sizeof can take an expression directly. So, okay, let's alignof and sizeof. Add sizeof and alignof. Okay, pointer arithmetic. So, additive operators. For addition, we can add a pointer to a complete object type with an integer type. Okay, and then let's add addition first, worry about subtraction later because it has more forms. So pointer and integer type can be added, and this is not important. Integer type is added, it results in a pointer, and we are like advancing it to the hypothetical array element is what this says. Okay. Yeah, it's just more words to do. Let's just implement it how I think it is and see whether or not that actually works. So we don't need to actually, so let's say we want to do sizeof. So we want to allocate an array containing 2 elements, and I want the first one shall be 11, and then the second one, so +1, shall be 42, and then we want to print the first one, and we want to print the second one. Right, and we're getting invalid type for binary operators right now because we're not handling that. So let's just look for a binary operator. So addition. We can add pointer and an integer type. So sizeof is pointer. The left operand is a pointer. Then the right operand has to be an integer. Right? Not signed integer, just integer. Okay. The right operand has to be an integer. Otherwise, if the right operand is a pointer, then the left operand has to be an integer. Otherwise, has to be an arithmetic type. I'm not actually checking, like we need to check both times, but we're not doing that. Otherwise, both have to be arithmetic types, right? Both are arithmetic type. So we actually need to check both operands. Right, the type. Okay. Right, and here both have to be integer types, I'm assuming, for the shift operators, integer type, integer type, integer type, integer type. So right also has to be an integer type. Great. So what happens now? Okay, we're getting an assertion failure in do usual arithmetic conversions. Are we doing the usual arithmetic conversions at this point? Okay, so we're handling this case. We are only doing if both have arithmetic type. Great. So so we're only doing this one if both are arithmetic type. Then we're doing the usual arithmetic conversions. Okay. Okay, now we're getting an AST, but we're crashing a codegen at some point. Yep. So codegen line 100 for addition. Okay, so else if we're getting the type of the result. So we need to compute the correct result first. Because right now the result of where do we do the pointer addition? Right here? No. Right here is signed in 64. Of the it's a pointer to signed in 64. Which is just a coincidence because we're hard coding the type to the type of the left operand. So we also need to set the type correctly here. So const sizeof type the result. Yeah, let's just call it type. So right here, the type is the, so it's always the pointer that gets the type. So here it's the type of the right operand. And here it's the type of the common, actually. We can't compute the result of this point because here the type is the type of the arithmetic conversions. Okay, this is a bit ugly. So let's not set the type at this point, but when we do the usual arithmetic conversions, let's say this returns type. Because after we've done the usual arithmetic conversions, both have the same type, which is then the type of our operand. So we have adjusted both operands to return the same type at this point, so just return it. And then right here we can set the type to do the result of the usual arithmetic conversions. Then we're doing here an assert that the type is null pointer. This is so ugly. Type should have been set at some point. And then we are returning that type right here. I'm getting an error message of the stream quality. Let me just restart streaming really quick. Okay, error message disappeared. Okay, so now we're getting the correct type. And during code gen, line 100, so if the result is a pointer, then we are doing some sort of pointer arithmetic. But we actually don't know which one. So we want to add like one pointer operand to the other pointer operand. But we don't know in which order they were pushed onto the stack. So let's actually go further and normalize it. So this function does way too much work. I mean, this is a little where we're cleaning it up. So at this point, what we want to do is swap the operand so that always the left one is the pointer and the right one is the integer. And then we know in which order they're pushed onto the stack. Right. So, is that a good idea? Can I do it easier here? Line 100, where you called, yeah, it's easier here. So at this point, I want to swap the operands, left and right. Right. We always want the pointer operand on the left. Okay. And then during code gen. Now I can do, wait, did I do that correctly? Yeah, we are having the exact same code as above. Okay. I'm getting the error message again. Okay, sorry, my internet doesn't like me apparently. So if we're having pointer, then we're calling a built-in b love lib memory address add. So this built-in adds an address and an offset. And we know that we pushed the pointer first and then the offset, so this is the correct operand. However, we also, the offset is in bytes, so, but we need to multiply it by the number of taps. So we push the size of the type. Point t type is node cast love pointer type point t type gen that type. So we want to multiply it by that size. For that, we push its size onto the stack. Point t type layout size. Love other int call built-in b love lib int u multiply love. So we're interpreting it as unsigned. Well, actually we need to interpret it as signed. So we do signed multiplied depending on our workflow. Right, so so the offset is on top of the stack as we normalized the expression, multiply it by the size of the type, offset the pointer. Okay, so what's this doing? It worked. So we are printing 11, which is net restored, and then we're printing 42. Great. And this is type checked. Not type checked, but we are bounds checked. This panics. Again, line 18, which is this one. And this panics because the implementation of this function so an address in love consists of allocation, generation, and offset. This function modifies the offset, but keeps the allocation index in check. So this adds the offset within that allocation, and when we dereference it, we can check whether that offset is still within the bounds of that allocation. So that is great. Let's also do the symmetric version of subtraction. So subtract pointer by integer, which is the same just with a different sign. So compiler, copy, right now we can do that. Add the same logic here. Shouldn't need to do anything for that, but in CodeGen, we need to handle a different sort of logic right here. So offset the pointer, but we want subtraction. Okay. And then let's try it out by doing subtraction of -1, which does the same thing. Subtraction of, so this works. Let's commit. Add pointer, addition, subtraction by integer. Okay. So the other version of subtraction is we can subtract 2 pointers and get the difference between them. But first, actually, like incrementing. Let's check incrementing. Whether this just falls out or whether we need to do more than that. So let's do something fancy like that, and then here we want to subtract the pointer. Okay, it does not. So we need to manually increment, decrement. Unary expression, right? This is somewhere arithmetic operation, unary op. Right here. So is arithmetic or is pointer? It's pointer child type. And now it works. Okay. That was easy because I'm pretty sure this is like I'm actually so curious how we handled it in during CodeGen, that it just worked out. Unary expression. We are calling the correct function. So we're calling the same function, which is why it just worked out. Okay, so that was a quick and easy fix. Pointer, increment, decrement. Let's add subtraction. So the other version that I want, where we take for subtraction, this one, both our points are pointers. And then this returns, so they shall point to the same array object we're going to handle that, and then it returns essentially the difference, in like, lots of words to say the difference between them. Let's add a complex test right here. So in diff pointer plus 1 minus pointer. Right, so, and this should be 1. But we're getting an error right here. So binary subtraction right here. So we actually, for subtraction, let's be fancy. is pointer left and is pointer right. Hi. In the stream, we are writing an interpreter for C. So, yeah. So if we are subtracting two pointers, then we return true, else we fall true, and do the same logic. Right here, and then we, interesting assertion, type should have been set at some point. Oh, right, this is the assertion, and then the type is the type of the, actually the type now is signed in 64 or something, right? The size, its type is pointed if t, which is signed in 64 in our implementation. State asked create sizeof built-in type signed in 64. Okay. Okay, so interesting. So let's see what's going on here. So we're generating like 1 line 100 or something right here. So the operand is subtraction, and the result type is a signed int. So we are handling this case because we are querying the result type, not actually the operand type. So if we look at the operand type, which is a signed int, then we're saying, okay, we're subtracting two signed integers. But this isn't actually correct because pointers cannot just be, like lauf addresses cannot be interpreted as integers for subtraction because they store the allocation in addition to the offset. So we're getting not the correct value. We're getting like a huge bit pattern because we are subtracting, like we're interpreting this address as an integer and then subtracting it, which is obviously nonsense. So we need to handle this case specially, which we can't just do by looking at the type. We need to look at the operands, but this function does not get the operands. Which I guess it sort of makes sense because, like, fundamentally, subtraction between pointers is not the same as the other kinds of operation. Because, like, for the other kinds of operation, the result type has something to do with the operand type. But here, the result type is completely decoupled from the operand types. So let's actually add a new kind of operation. Let's call it let's call it pointer. Yeah, it's called pointer diff. Subtraction pointer. And when we reach this point, we change the operand to pointer diff. This is unreachable, not an operator that is passed. And then right here during codegen, we add a new case right here for the operand pointer diff. And here we're calling a built-in that we already called before for pointer comparison, memory address distance, which returns the distance between two operands. Right, so, but this does, yeah, so this is the pointer operand that we're calling. We're getting an error right here because arithmetic op does not have this. Let's do, so this function is also called for compound assignment operators, but they don't have that one. same be up. So we need to seal out binary arithmetic up if up pointer diff t return like so. And we want to call built-in. And here we need to handle this during print. Pointer diff. Let's call it like so. Okay, and so somewhere in here we're doing a difference between pointers, and we're getting a difference of 8. This is because the function gives us the difference in bytes, but we want the difference in size units of the type. So we need to do a division, get the difference in bytes, convert that okay, and this is where we actually need more information, because we don't have it. So we need to get the type of the pointy, which we do not have. Okay, so we need to restructure the, so it does not take, it takes an expression, so it's operand of an expression. Let's get that in addition. So expression type. And then here we're passing the expression directly instead of its type. And also here. And also here. And now we can do the division. So the pointy type is the of like any operand type. Right? And then we want to do a division. So assigned division, I call built-in now lib int signed division, which can overflow if we subtract int min by -1, which we are never going to do, but that's okay. Why are you triggered? Oh. So this is also called for increment. Decrement also passes an arithmetic up here, so this branch is reached, but we never actually reach this one. So, and now we're printing 1. Great. And that is pointer subtraction to get the offsets. Add pointer difference. Yeah, let's call it that. Okay. Then we also need to probably handle compound assignments. So something like that is not handled. Assignment up right here. Then we're doing assignment conversion. Right, pointer assigned to pointer. What actually does the standard say at this point? So assignment, compound assignment, let operand shall be blah, blah, blah. Do we actually check that ever? We don't actually do the type verification of assignment. Okay, so let's first thing first, we allow assignment pointer integer. Is pointer, so the target type is a pointer, and the type of the value is an integer. And the we would doing a compound. So we need to figure out whether or not we're doing a compound here. Yeah, so we need to get the operation that we're doing, sizeof assignment op. Op has to be sizeof assignment op add or subtraction, and then we can just return the value unchanged because we don't actually need a conversion. And then here the assignment of is none. Here the assignment of is given. Here the assignment of is none. And whatever this is doing also doesn't do any compound assignment. And now this should just fall out because we're reusing the same code. So this works, and we are doing like a compound assignment here from a pointer with an integer. Great. Support compound pointer assignment. Next up, we should probably really quickly just, when we do assignment here, we should probably check for the property for compound assignment, and the either, so for plus and minus, we shall have pointers and integers, or both arithmetic, and for other arithmetic, yeah, it should be consistent with those a little bit, the corresponding binary operator. Yeah, let's not worry about that. Let's do that some other time. So let's don't type check those. Instead, there's probably a bug in the implementation of pointer comparison. So now we can do, let me clean this one up. So pointer, second pointer, pointer plus 1, if pointer kleiner. So comparison between pointers. Let's actually print that. That's it. Okay. This is probably going to give the wrong result. I must guarantee that that's going to give the wrong result. Oh no, it actually, really, it prints, okay. Because we're getting like a to-do here, the sign is probably wrong, but apparently not. So the implementation last week, we couldn't test that because we didn't have pointer arithmetic. Why are we crashing though? Oh, I know we're not crashing, we are getting, so we're returning 70 because we reached the to-do. So that actually turns out the implementation was correct after all. I honestly did not expect that. Codegen 556. So we need to check that. So we are computing the distance and comparing it with 0. So this is the same deal, where I cannot do something like compare second, cannot, so in local. So this one will crash because we are comparing 2 pointers, right? But the actual comparison was correct. Okay. Remove to do since comparison is correct. Okay. So we've got pointer. If you have pointers, we can dereference them. We can do arithmetic. So let's add the operation that does this at once, which is the array access operator. Yeah, array subscripting. So this works on pointers, and this is defined to be equivalent the one expression added to the other expression and then dereferenced it. So this is like a really weird form of expression. This is some kind of binary expression actually. So let's add that to. Nah, we can't. So what's a convenient way of putting that? So we've got the unary expressions, like which are just ungrouped, and here we have dereference, and here we've got like generic binary expressions. Let's actually do like a synthesized thing. Like it's defined to be equivalent to that, right? So let's just generate the same AST, right? That should be convenient. Then we don't need to touch that anywhere else. So when we actually do, that's really smart actually. Okay, so we are parsing, this is like a postfix expression, right? Yeah, and this postfix operator. So we're parsing the postfix operators in here, and let's just add a new operand like so. And if we have that, then we want to pass an arbitrary expression. So I can actually just do DSL square bracketed DSL recurse expression. Right, so. And let's see what sort of, I don't know what's the argument, so we're getting like a function argument somewhere in here, right here. So we get a similar kind of operation for this one. Compiler state. So we're getting the pointer, the operand, and then the index. This is called for pointer index. And then what we want to do is we want to build like the same AST as that other one. So we want to do offset. So we want to create a sizeof arithmetic expression on that location. Pointer type. Let's do it like so. So a pointer type. Then the whatever the elements. Pointer index, I guess. And then we want to dereference. But for that, I can call a helper function, create unary state sizeof unary of dereference at that location. Take that offset. Oh, the other way around. And that should be it modulo some test that we need to do. So pointer 0, 11, pointer 1, 42, print, pointer 0, pointer 1. Right, of course I need to also specify which kind of arithmetic, which is addition. Addition. Okay, I'm missing the, let me look up the constructor arguments. So we've got type, first the type. Pointer type. Okay. Right here, and this just works because we're just reusing the existing code. And because this is like defined by the standard to be equivalent to what we're generating. So as we can see in the AST, what we're generating is, for example, here the assignment, unit expression, pointer, indexed by ones. So like addition and then dereference, just as the standard set. And because this is entirely equivalent, we can also write it like so. Except that apparently we cannot. Right. In principle, however, because then we would need to swap those. And we're also not doing, so we need to swap pointer to index here. And we also need to do the checks. So let's do the checks. So, so first of all, let's normalize it and say that this is not a pointer. Then we're swapping pointer to index. Normalize. So pointer is always the left argument. And then the standard has a bunch of constraints here, I'm assuming. Yeah, one shall have pointer, shall have integer type. If not sizeof is pointer, so even after normalization, pointer is not type, or the other one is not integer, then we're having invalid types. Invalid type, so let's copy this one. So diagnostic invalid type for subscript operator. And now it even works with swapped arguments because this has been normalized by our swap. Okay. Let's commit that. Add pointer subscript operator. And finally, the standard says a bunch of code like pointer to complete object type for all those operations. And we're only checking for pointer. So let's add a helper function is pointer to complete object type. So if not is pointer, then we return false. Otherwise, we return is complete object type, cast it to a pointer, type, pointy type, yeah, like that. And then we're doing a bunch of checks for expression. So somewhere in here with everything will do. So increment operator requires is pointer to complete object type. Dereference, I guess, also requires a complete type. No? Interesting. So you can dereference an incomplete type. Okay. The standard says so. Is pointer to complete object type. Is pointer to complete object type. Pointer to complete object type. Is pointer to complete object type. Is pointer to complete object type. Comparison. Well, I guess equality does not, but relational requires. No? Okay. Interesting. How can you compare it if you don't know the size? Okay. Okay, that's that. And now we should no longer have to worry about code like this. Where we do stuff like void pointer like so. I don't mean to. This should not trigger an error. It's a common extension that this does. It does not trigger an error. Why am I not triggering an error? How are I interpreting that? So verbal declaration before the print. Wait. The operand of the cast is, I believe you're parsing that wrong. Yeah, it's a unary expression, not. Okay, so let me parenthesize this one, and then we fix the casting bug. Right, invalid type of binary operator, and then we're crashing because of that assertion. So this is line 871. Because right here, so we just set the type to something. Okay, just so that we're not crashing. Okay, invalid type of binary operator. Check that pointer arithmetic is done on complete. Oh, I know. Comparison does not require a complete type because we can do it, but just by comparing the bytes. So we only require the complete type every time we need to do here during CodeGen. Right here we need to know the size of the type so we can divide. Here we need the size of the type so we can multiply. But for comparison, we don't actually need the size of the type, which is why it does not require a complete one. But let's fix the parsing bug for expressions. So after the operand of the cast expression, we are recursing and parsing a unary expression, which is supposed to parse a unary expression and not. Okay, but this could be a bug in Lexi, so I don't get into that. The stream is already at my endpoint anyways. Okay, so thanks to everybody who stopped by. We did a lot. We essentially implemented pointer arithmetic. It's 1 hour stream with pointer arithmetic, but that's okay. We've got a lot of pointer features done. The next thing is to add arrays, right? So we don't need dynamic memory allocation, just so we can try out indexing. But before the size of the array is a compile time constant. So what we are going to do next stream is start implementing like constant evaluation of expressions in preparation of arrays. This is also so currently global initializers are not supported. They're not initialized because we also need to generate do compile time evaluation for those. Okay, but that's a plan for next time. So thanks for stopping by, and until then.